Good afternoon, good morning, good evening, wherever you are. Thanks for joining this webinar. Today's webinar is from PCTEL about interference hunting. On this webinar today, we have three presenters. First is James Zig. He's the Director of Product Management here at PCTEL, RF Solutions. Jim has a vast experience in the field of telecommunications. His experience is around more than 20 years, consists of both the front haul and the back haul network. We also have on this webinar today, speaking with us is Mark Gusen. He's a product marketing manager here at PCTEL. He has a 10 years experience as an RF test engineer and currently is responsible for PCTEL's Seawave product and the CW transmitter. Myself, I'm Chintan Fafadia. I'm a senior product marketing manager here at PCTEL, and I manage the scanning receiver line here at PCTEL. Before we get started with the webinar, a few housekeeping items. First, this webinar will be available as a recorded version later on. We will provide the link to all the attendees, and it also will be broadcast on YouTube. Secondly, we'll take questions towards the end. So please put in all your questions through the questions field on your webinar dialog box, and we'll answer questions at the end. We'll keep around 10 to 15 minutes at the end to answer the questions. With that said, I'll now hand it over to James Zig, who will talk to us more about interference and introduce different types of interferences.
Hey, thank you, Chintan. And again, I want to thank everyone for joining us today. What I want to cover today are first the interference overview, followed by describing the types of interference that you might encounter when you're actually doing interference hunting, explain a little bit about radio propagation, then actually talk about interference hunting techniques, followed by an introduction to what our Seawave interference locating system is. And then Mark will finish off by actually looking at a case study of an interferer that he actually had found. So moving to the next slide, I want to first cover our interference overview. And what I really want to do is kind of give an explanation of what interference is. Essentially, it's an unwanted RF signal that can be caused by various electronic sources that affect, in a negative way, mobile communications or whatever type of electronic signal that you might be using for communications, whether it's mobile or not. And this can also include harmonics. And the frequencies that are most affected by interference, well, all frequencies are really affected by interference, but typically because of the radio propagation of lower frequencies which travel a lot further, you usually have more interference hunting going on in the lower frequencies, like in the 300 to 900 megahertz range, as opposed to the higher frequencies like 2100 or 2600, where they don't propagate as far. But interference affects all frequencies, so consequently, in the end, you'll probably be hunting interference at all frequencies. It's just that you'll be doing a lot more of them at the lower frequency levels. So the effects of interference, going to the next slide, they can cause a lot of issues in a mobile communication network, including video pixelation, which we're showing here on the right-hand side, poor voice quality. It can be dropped calls or drop sessions if you're in a data session. It can also cause low data throughput, extremely important, not having that when you are into smartphones as you are in industrialized countries. And latency due to retransmission, particularly in a data network. And the business effects of this can be customer churn. And if you look at recent surveys of customer churn, about 25%, where you have between 25 and 35% of customer churn is actually attributed to the radio access network. About 25% when you have 2G, 3G phones, and when you have smartphones, closer to 35% of why people actually switch networks. And this actually can translate into billions of dollars. And this is not only caused by interference, it can be caused by coverage as well as capacity. But interference is can have an effect on this. And again, this can lead to billions of dollars when it comes to a large carrier and lost revenue if they lose customers because of this. And when really, moving to the next slide, when is the best time to really test for interference? Well, typically you test 2 times. First, when you're doing spectrum clearing, when you have new or refarmed spectrum, when it becomes available. Because what you really have to do is go in there and clear out the uplink and downlink. And typically the uplink interference probably has already been cleared if that frequency has been in service, because you can see uplink interference a lot easier. And when they turn off a network, the downlink is now available without having a large signal being transmitted from the tower. So consequently, you typically find a lot of interference in the downlink also when you're doing spectrum clearing that needs to be cleared out a lot more than the uplink. And then in service, kind of what I alluded to before, is that you typically look for the uplink, and this can affect the quality of service in a live network. And as you can see in the spectrum chart here from the FCC in the US, there's really a lot of spectrum available that is, I shouldn't say available, but actually is quite used. And consequently, with limited spectrum, you really need to get the maximum amount of throughput that you can out of any mobile network that you may own. So moving to the next slide, I want to get a little bit more into mobile networks and what their sensitivity is. So if you look on the left-hand side of the chart, you can see that there's a macro cell here. And they typically transmit around 45 to 46 dBm. And the sensitivity, it's actually higher than this, but this is typically the sensitivity, the -102 to -105, when an operator actually sees some type of interference hitting the tower at -102 to -105. You start checking the uplink to see if, what that interferer is doing, if it's levels up to about -102 to -105. And if you look down at the UE, it transmits at a lot less power. It transmits at about 23 dBm, about 0.2 watts, and a sensitivity, down around -95 dBm. And again, it's actually higher, but this is what could cause interference. But typically, when you're in service, the operators will look for uplink interference, and the reason for that is because if I'm only transmitting at 0.2 watts from the UE, I can have a lot of interference that hits that tower. Say that interferes at 2 watts or 1 watt. It's going to really cause a lot of havoc with that UE signal coming from the on the uplink. So typically what an operator does is they look at the KPIs in the base station, and they'll find out if they have some interference above -102 to -105 in that sector, or they may have a customer that's actually reporting a problem in an area, and then they'll go out and actually search for that interferer with a technician to find out where that is. The important thing to know is that new sources of interference are continually being generated. So even though you may clear out some interference when you're doing spectrum clearing, and you may clear it all out, you have new interferers that pop up every day, particularly in very crowded networks in dense populated areas. Now on the downlink, once the network is in service, because you have this large signal of 45, 46 dBm coming from the macro cell, it typically drowns out a lot of the interferers. And unless that interferer is really large, you're not going to be able to see that interferer typically in a downlink in-service network. But again, now with small cells starting to take off, and they're only transmitting closer to about 2 watts instead of 20 watts like for an ODAS system, or 45, 46 watts for a macro network, you're probably going to start to see a lot more interference hunting also going down on the downlink when it interferes with a small cell. So let's move on to the next slide and talk about actual interference mechanisms. So what I want to cover here is what I've did is I've divided these interference types into various different sources. As you can see here, we have modulated sources. I divided them into unmodulated sources. You can have interference caused by harmonics, passive intermodulation, as well as repeaters and bidirectional amplifiers, also known as BDAs. And then lastly, intentional interferers. So what a modulated source are caused by devices that are actually intended to transmit RF signals. So in this case, this would be like a walkie-talkie that's pictured here, or it could be a Wi-Fi access point, or some other device, another type of network, that is operating. and it's actually putting out unwanted interference that occurs when these devices are acting improperly or malfunctioning, or actually the operator is improperly using them. And often these are usually narrowband signals coming from these devices when they're operating improperly, or if they're operating through malfunction. And even though you may have compliant, in fact you will have compliant RF transmitters because they usually have to go through FCC testing, they can still create interference via harmonics or even through intermodulation. And particularly if you have something like AM/FM signal or something like that, it could be useful also to be able to demodulate these signals to ascertain where the source of that interferer might be. Moving to the next slide, I want to now talk about unmodulated sources. And these are sources of interference that, again, are created by electronic devices, but they actually create unintentional RF signals. And these can be actually split up into two separate categories. One can be continuous noise, and another category can be impulse noise. So the common sources of continuous noise interference and sources of that could be from electric motors that operate continuously. They can be the ballast and neon signs, and even neon lighting. Faulty transmitters and faulty transformers, I should say. Security and infrared cameras, and vehicle and ignition systems. And what I have shown here on the bottom side is a plot of a spectrum actually in the 900 megahertz range. And what you can see here is when a motor is turned on the right-hand side, it actually causes wideband interference that raises the noise floor throughout that whole spectrum. So consequently, your signal-to-noise ratio goes down. And as a result of that, if you are operating on this, let's say you're doing a 900 LTE in some parts of the world, you're probably going to get a lot less throughput here because your signal-to-noise ratio has just gone down because this motor has caused this interference in the spectrum. So on the next slide, I'm talking about unmodulated sources. And this is impulse noise from unmodulated sources, and these are created when you have the electricity flow turned on and off to the device that's causing this interference. And the common sources of these impulse noises can include electric motors when they're operating, let's say, in an elevator where it goes on and off depending upon when the elevator is operating, manufacturing plants, farms, and the like. They can be caused by electric fences which turn on and off so cattle don't get hurt by the electric fence, welders, parking gates. We've seen a lot with actually baby monitors for some reason. Wireless speakers is another common source of these unmodulated sources of interference. Arcing power lines, light dimmers, light suppression devices, commercial baking ovens. Ironically, the beacons on the top of cell towers is another interferer that was actually found to be causing interference in their own mobile network. Garage door openers and TV remotes, and the list goes on and on actually. So pretty much any electronic device that you use intermittently could be a possible source of unmodulated interference. Another source could be harmonics, and we probably all know what a harmonic is, which is a multiple of an RF carrier of the fundamental frequency. So for example, if I have a 750 megahertz frequency, you can produce harmonics at 1500 megahertz, 2250 megahertz, 3000 megahertz, 3750, and so on. And even though we have large transmitters that are operating at TV stations, which can actually cause interference, even though they're legal, through a 1 watt harmonic if you're very close to the tower. So for example, if I have one of these old UHF channels that are operating 570 to 585, and these are channels 30 to 33, that could cause problems on the uplink in the AWS band in the 1700 to the 1755 megahertz band if you're very close to that TV transmitter. And this can be as large as a watt which would be the third harmonic that would be actually operating in here. And I kind of have an example of a harmonic here below. So if you look at the left-hand side, again, of the chart that I have, and I'm looking at a spectrum in the 900 megahertz range, and what I have is a walkie-talkie actually that's legally operating at 462.5 megahertz. And as soon as I start transmitting, it puts a harmonic in the 925 megahertz, as you can see here on the right-hand side, where the whole noise floor has been raised. And in a mobile network, so for example, if you're at an LTE network overseas and I have a US band walkie-talkie and on vacation I take it overseas, that could actually cause a problem with the LTE network in a country that's operating 900 LTE or whatever mobile frequency or technology they're operating in that 900 spectrum. Another common source of interference are repeaters and VDAs, and this is actually a very common source. And they're really only common when you have a malfunctioning repeater or bidirectional amplifier. And a lot of these were added in the 80s and 90s, even in the 2000s, in order to be able to boost mobile signals, both in building and even outside. So there are a lot of them around, and a lot of these networks are actually being turned off and refarmed over to LTE, but these repeaters and VDAs are not being turned off. So when you have a malfunctioning one, and since the age of these are pretty old, they can be anywhere from 5, 10, 15 years old, they can start malfunctioning, and they become a very common source of interference. They're also very difficult to locate. And Mark is actually going to give you an example of one that he hunted down here just recently, where an old VDA was operating and causing an interference problem for another mobile operator. Another very common source of interference, again, also is passive intermodulation. And this is when two or more strong signals combine, and they can create a nonlinear effect into your spectrum. So essentially what happens is you have this interferer, and you get the addition and subtraction of this fundamental frequencies coming from that source. These harmonics add and subtract and cause they can cause peaks, they can cause interferers at almost any frequency. So it's often called the rusty bolt effect because this is where early passive intermodulation was found, but it's really generated by a lot of different sources these days. And they generate these spurious signals that are radiated from these connected metal objects. And the common sources of these can be rusty bolts, as I have shown here. They could be fences or barn roofs, corroded rooftop air conditioners, improperly connected loose or dirty connectors in the cell tower antenna feed lines, or let's say if you're in a DAS system in building, if they're improperly torqued. They can be cell tower guy lines. They can also be utility poles or rain gutters. They're actually finding a lot of interference now for in-building DAS systems. So you have to be very careful where that antenna is placed, because if that antenna is placed near some metal ductwork or some I-beam girders, you actually can get PIM that's being created by the signal being transmitted into that metal girder, that metal ductwork, and then combining to cause all these different frequencies and harmonics of these frequencies that cause passive interference. So it's actually starting to become a larger problem on these in-building systems than it is even on these macro cells that we have today. And then there's also intentional interference. These are actually caused by devices intended to cause interference, such as the jammer. And they're actually located in shopping malls, restaurants, schools, military bases, usually where there are a lot of people. And the sources could also be mobile. They can be in cars and trains, buses, any moving object. Civilian use is illegal, but people still have them. They're available on the black market. They're usually typically easy to identify, they have a strong constantly on signal. They usually raise the noise floor as shown here in the chart below. And a couple examples of this are like a school teacher didn't want her children to use cell phones during class, so she actually deployed a jammer inside of her desk in the classroom. And we've probably all heard about the driver in Florida who didn't want people using cell phones around him while he was driving, so for 2 years he operated the jammer out of his car. And it took him about 2 years to hunt him down, and the FCC is fining him $48,000 for the use of that illegal jammer. So now I'd like to move on to radio propagation. We've kind of got a good feeling now of what the sources of interference are. And if you look at radio propagation, you find that all spectrum is not created equal. So when you have higher frequencies, and this is approximate, if I have 15, 1700, 1900 megahertz type of frequencies, they're typically more disposed to be more line of sight and more easily reflected off of buildings and vehicles with very low penetration into the building itself. Now if you have lower frequencies, and again you're under the 1500, 1700, 1900 megahertz, they tend to bend around objects a lot more easily. They have much better penetration characteristics into structures, and they travel a lot further. So they're much more useful typically for coverage as opposed to capacity. And the range of the signal, say you have an interferer that can be detected, is dependent both on the frequency, as I'm showing here, depending upon what where that interferer lies in the frequency spectrum, as well as power. And to give you an example, if you look down below at the chart, you have a 2600 megahertz network and a 700 megahertz network, and you need about 7 to 9 cells to be able to have the same type of coverage you do with a 26 megahertz network as you do with a 700 megahertz network. So hence I mentioned earlier in the webinar that you do a lot of interference hunting at lower frequencies, and it's because of this distance that these lower frequencies can travel versus a 2600 megahertz signal, which will travel a lot less further than what a 700 megahertz signal can travel. And then there's radio wave multipath. And multipath occurs when the radio signals from a source reach the receiving antenna via multiple paths. It give you 2 or more paths. And this is caused by both reflections as well as refractions off of bodies of waters or objects, including buildings and mountains and the like. And this is what you actually get in urban canyons and downtown areas. It's actually something you like to have when you have an LTE network, because most LTE networks use MIMO, and MIMO really depends on reflections in multiple paths to be able to get higher throughput values in the network. So consequently, even though it's very desirable when you have an LTE network, it's very difficult to be able to hunt down interferers when you have a multipath condition. And this really severely complicates locating that source of the interferer. So now I want to actually move on to interference hunting, now that we kind of understand radio propagation and types of interference. So when you want to be able to detect interference, you need some equipment such as a spectrum analyzer or an FFT scanner. And both are actually used successfully. Some spectrum analyzers, in fact most of them, you have to specify a lot of parameters, and it takes a lot of effort to set up the spectrum analyzer, whereas with an FFT scanning receiver you usually have just a few settings to be able to operate it. And some spectrum analyzers use a heterodyne principle. This is the more of a hardware type of architecture where they be able to sweep the signal throughout the frequencies. And with a heterodyne type of spectrum analyzer, the information may be missed during the sweep because it operates typically slower than an FFT scanner, and you have typically lower dynamic range over large frequency ranges. Now, with an FFT scanning receiver, the sample is digitized and then an FFT is actually applied. You have a much higher probability of intercept. And you would have better dynamic range over large frequency ranges than, let's say, a heterodyne-based spectrum analyzer. And when you detect interference, you need a directional antenna. And there are two types of directional antennas that are typically employed while hunting interference. One is a log periodic, as shown here in the upper right. And the reason this is used is because it has a wide frequency range, several gigahertz. So I usually only need one antenna, one type of antenna, to be able to look at all the bands that I have in my mobile network. The downside of it is it's less directional than a Yagi antenna. So with a Yagi antenna, as shown here in the lower right-hand side, these are frequency specific. If you're at a lower frequency, they typically have a very narrow bandwidth, maybe 15, 20, 30 megahertz. Whereas if you're at a higher frequency, maybe at a 25, 26 megahertz frequency, you might have about a 250 megahertz bandwidth with this antenna. The advantage of it is it's more directional than a log periodic, so it's a little easier to hunt down the interferer. The downside of it is I have to have multiple antennas to cover my my mobile network if I want to hunt for interference in every one of the bands that I might have. And then when you're actually using and doing interference and using these antennas, you have a couple choices. You can either set the antenna in a horizontal orientation or a vertical orientation. And these have different polarizations. So if you look at the chart below, you can see the elevation radiation pattern. You see it's a lot more directional than what the horizontal orientation is, where you have the azimuth here. And you can see actually that it has a much wider spectrum, or radiation pattern, I should say, throughout the angles at which you pointed at. So often what users do is they use the vertical polarization. It kind of depends upon what your interferer is like. So for example, if your interferer is a BDA with an antenna, it might be putting out a horizontal or it might be putting out a vertical orientation of the radio signal. So consequently, since you don't know what the interferer is, what some of the interference hunters do is actually turn that antenna at a 45-degree angle. So they kind of split the difference between the elevation and the azimuth when they're hunting for their interferer. And then there's locating interference. And this is essentially where I do triangulation to be able to hunt where the source of that interferer is. So essentially what you need for this is a map with a compass built into the interference hunting system with GPS. And what I can do now is if I take 3 or more bearings, I can actually triangulate where the source of that interferer might be, which makes it a lot easier for hunting interference and the location of where it is when you're out in the field and trying to do this very quickly. But then there are challenges when you're trying to locate interferers when you have a multipath condition, such as in urban canyons. And when you're in an urban canyon, as shown here on the right-hand side, the best thing to do is to try to find a location away from buildings and metal objects to be able to get less reflections, such as like a building roof or away from metal objects like a vehicle. This will help in trying to locate where that interferer might be. But even with that, you'll still have a lot of multipath. So consequently, what we found the best thing to do is to go to the middle of an intersection and then point in all 4 directions of where the streets are, and then follow the signal down the street where you have the largest dBm from that interferer hitting the antenna. And then you just follow that to the next intersection and repeat the process until you finally come to the location where you have to backtrack on yourself, and that's probably where that interferer is on that street, where you have that highest signal back in the direction that you just came from. So with that, I'd like to turn this over to my colleague Chintan Fafadia to actually talk about the Seawave interference locating system.
Thank you, Jim, for the introduction into interference, for the overview of what type of interferences occur for radio propagation, and setting the talk towards how do you hunt down interference. Now, interference is a real problem. Carriers are seeing them all around the world more and more with the LTE deployments in and around the 700 bands or the lower bands. Interference becoming a real problem, and it's become a bigger problem day by day. To hunt and locate this interference is not completely a science. It's an art too. So while it is required to hunt the interference, you need tools that can make it easy, but it's an art too. So as PCTEL, what we have done is we have tried to create a tool which is easy to use for the end user to help them identify the source of the interference and locate it exactly where it is coming from. And at the same time, it's making it very ergonomic, easy to use, so that they don't have to deploy too many resources. Carriers are already strapped on budgets and the number of people that they have at their disposal to use for optimization or other network tasks. So adding on an interference locating system, which would be complicated, would just make things more difficult for them. So with that said, I would like to introduce the Seawave interference locating system and take you through how this works. So the basics of the Seawave interference locating system is that it uses an existing scanning receiver. So if you have a PCTEL scanning receiver, whether it's a PCTEL Seagull EX, MX, EX Flex, or the new IB Flex, you can use any of these scanning receivers with the Seawave system. The way it works is that all the scanning receivers have a spectrum analysis option built in. So we decided to harness and leverage that option to help users identify and locate interference. So if you have that spectrum analysis option, you can turn any scanning receiver into an interference locating scanning spectrum analyzer. What we did is, to make it easy to use and handle, you combine this with a battery pack, put it in a backpack, and you can walk around with it, and you add on a handheld host platform to it. So the purpose of the host platform is threefold. First, it connects to the scanning receiver and all the other components, so it kind of becomes the heart of the entire system. It connects to the antenna, and it also loads becomes a loading dock for the tablet, which hosts the application for Seawave. So the host platform internally, it also consists of a digital compass, a preamplifier, and a trigger button to save bearings. The third and the important part of this application, very important part of this application, is the software application, which resides on a Windows tablet. It's a touchscreen application, very easy to use. So again, we are trying to make this art of interference hunting as easy and as scientific so that users don't have to spend too much time in locating and identifying interference. You combine this entire system with a Yagi or a log periodic antenna, and you get an interference locating system. So very beneficial. So in terms of features of the Seawave system, let's go through the benefits of using this. First, it's very ergonomically designed. It's designed for one-person use. One person can carry the entire scanning receiver in a backpack with the battery pack, use the Seawave handheld system in one hand, and use it with the tablet. So you do not require two people to identify interference. That saves cost, time, money, resources, and makes it easier for anyone who is locating interference. Secondly, this is not only limited to your internal interferences, but also to sources beyond your existing bands or external interferences. So you can identify both interference and internal and external. Like PCTEL scanning receivers can go from as low as 150 megahertz to 6 gigahertz. So you can use this entire frequency range to locate interference. Third, the system has a very long battery life. So first of all, it's lightweight because the scanning receivers are not very heavy. Second, the handheld host platform is not heavy. And third, it gives you a higher battery life compared to spectrum analyzers, the traditional spectrum analyzers, which weigh more than 20 pounds or so, and the battery life is very limited. In this one, your battery life can go the PCTEL scanning receivers come with a hot swappable battery system. So in theory, you have unlimited battery life if you have enough batteries to go with it. And secondly, you can use an extra battery with the tablet to increase the battery life on a tablet. Without that also, it gives you a battery life of 4.5 hours or so. So it has a lot more longer battery life than a regular spectrum analyzer. And fourth, it's optimized for touchscreen. So the software application is built on a Windows platform, Windows 8.1 platform, so which is very easy to use, and it's optimized for touchscreen. The application is basically, you set up a scan, you look at your interference, and you take bearings. So as simple as that. Another important thing, it gives you accurate location of the source. So traditionally we say that this system can help you identify the source within 150 feet, which is pretty good for interference hunting, because generally when you start with interference hunting, you know that it's in one of the subsectors or sectors of one of the cell site, and then from there on you start looking for interference, either it's uplink or downlink. So it helps you narrow down and gets you within 150 feet of the source. And the most important benefit or feature is it's cost effective. First of all, you can use your existing scanning receivers, so you don't have to buy a separate spectrum analyzer. It's very cost effective, and it reduces cost, and the return on investment on your scanning receivers goes higher. And combining it with the host platform and everything, it's very cost effective. So these are the features of the Seawave interference locating system as such. I would now like to walk into the spectrum analyzer benefits of this system. So what it has that compared to a traditional spectrum analyzer, it has all the features that you'll find in a traditional spectrum analyzer as well. First thing, we have an inbuilt preamplifier within the host handheld platform. What this helps is that if your interfering source is pretty far away and very low power, it will actually amplify it up these signals by up to 25 dB. So you can easily look at the source and it doesn't get lost in your other signals. Secondly, if you're very close to the source, we also have an attenuator built in the host handheld platform, so it doesn't drive the scanning receiver towards saturation. So it's taken care of both the aspects. If the source is far away, we have a preamplifier. If you're close to the source and it's very high powered, you have an attenuator. We also combine a GPS antenna and a digital compass within this handheld platform. So this is required for accurate lat-long location and also determining the direction in which the source the interfering source is coming from. With traditional spectrum analyzers, one of the biggest benefits, or with any spectrum analyzer, the benefit lies in how low you can go in terms of your resolution bandwidth. With this system, the minimum possible resolution bandwidth is 5 kilohertz, and you can go up to 80 kilohertz. So depending on how wide you want to see or how narrow you want to see into that signal, you can set up the resolution bandwidth as required. On the screen also, we have options like min, max, and average hold. This helps you monitor the interfering source in a very easy manner. So you can see that what was the minimum level for that particular source to the maximum level. And with different colors displayed on the application, it's very easy to differentiate and see that how the source is varying in its power and what if it's time-based or how things are changing. The last and important thing is that we have an N-type connector on the handheld host platform. The benefit of that is you can not only use the antenna that is provided by PCTEL, which is the log periodic or Yagi antenna, but you can get any off-the-shelf antenna. So if you are doing a very narrow band interference hunting for a particular band of frequencies, you can pick up off-the-shelf antenna for that particular frequency and start doing your interference hunting with that, because this can connect easily to the PCTEL Seawave system through the N-type antenna connector. A little bit more about the application itself. There are two major screens that help you identify the signal in terms of its power level. So what we have done is we have divided them into a traditional spectrum scan and a spectrogram. So on the spectrum scan, you can watch all the frequencies. So you can start with a wideband frequency and have your interfering source as a central frequency. Now if you want to narrow it down, you can narrow it down to a selected frequency scan, which helps you lower the resolution bandwidth and get closer in terms of your frequency with the interfering frequency. The second and the biggest benefit is we can do 2 scans at the same time. So if you want to do interference hunting, suppose on uplink and downlink at the same time, you can set up these scans and you can do these 2 scans simultaneously. So you do not have to do 2 rounds for 2 different bands, which generally traditional spectrum analyzers do not offer. They can do only 1 at a time. So it saves time and money again. You can always use the marker. It has a prominent blue colored marker which coincides with the center frequency or the interference frequency. So you can use this marker, move it around if you think that the frequency is different. And each scan that you set up has independent collection and scanning capability. So combined, the spectrum scan charts also show you the power level varying for the center frequency along with the x-axis where you can see all the different frequencies and the powers on them. Another chart that we also have is a spectrogram. The spectrogram is nothing but the time view of your spectrum chart. So chronologically, how the interference is affecting the network or what is the power level you see through this spectrogram. Very easy to understand because you can set up your own colors and legends. So to distinguish, if I want a particular interfering levels to be red, I can set it up red. And if you look chronologically, if something comes red through the screen, that means the source of interference is there throughout the time and it's easy to identify. This could be especially useful if you see that interfering sources are intermittent. So they're not coming up throughout the time or only coming at some time during the day. So you can set up your spectrum analysis on the scanner and then watch what time of the day this interfering source is coming through the waterfall diagram or the spectrogram. Another aspect of looking at, once you have known the frequency which is interfering, now you want to locate where this is coming from. So the Seawave has inbuilt maps along with the trigger modes, 2 different trigger modes that help you identify the location of the interfering sources. The first mode is a manual mode, which is pretty straightforward. You point in the direction of the interference, you press the trigger, and you take a bearing. So at that time, when you take a bearing, it records the latitude and the longitude of where you are and the direction in which the source of interference is. That is one way of doing it, which is called a manual mode bearing selection. The other way of doing it is, if you don't want to do a manual mode or you want to be sure that your interfering source is coming from a particular location, you can do an automatic mode bearing selection. What you do with that is you put your application in automatic bearing mode, you press on the trigger and you hold the trigger for a set amount of time, and then you move your antenna in 60 degrees both ways, to your left and to your right. So that way you're doing actually a 120 degree or 180 degree semicircle and trying to locate in what direction is the strongest power level for the interfering source. So after the set amount of time, the application automatically determines in which direction the power was the strongest and it takes a bearing. So this kind of removes possible human errors and helps you be more sure that your bearing is in that direction. It's automatically calculated. So what you do is you take these bearings from 2 or 3 different locations and then you combine them on a map which comes inbuilt with the Seawave application system, and then you can triangulate. So once you have 3 or more bearings, you triangulate these bearings and you can see where the source of interference is. So it makes it very easy. Even if you have done recordings over different period of time, you can combine bearings from multiple sessions or different sessions, bring it into a single session and do triangulation at the same time. So inbuilt maps along with different bearings can help you identify exactly where your interfering source is. So that was an introduction or a primer into the Seawave interference hunting system. And as Jim mentioned, there are so many cases which have been recorded for interference like this. A few examples that we have cited here is one was where Verizon, one of the 700 LTE site from Verizon was a victim of fluorescent lights, and actually this had FCC get involved, and they got involved and helped Verizon fix this issue. Another one was where one of the LTE sites was affected by a Time Warner cable box, which was a Time Warner cable box was affected by LTE site. So there are many interfering references or sources of interference. There are other cases where people have been using jammers in the cars to avoid people next to them to talk on the phones. So this is a bigger problem, and it is becoming bigger and bigger day by day with the amount of frequency spectrum that we are using for cellular now. So with that said, I will now hand it over to Mark, who would talk about a case study that we did in with one of the tier 1 operators here.
Thank you, Shenton. Hi, everybody. Let us conclude this webinar with a case study. A few weeks ago, we were approached by a tier 1 carrier in the US for a solution to locate interference sources. As we introduced Seawave, they went further by asking us to demonstrate our solution at a site which experienced interferences. Having noted a high frequency of drop calls in the area, engineers from this carrier conducted several field tests, including drive tests, of course, and were able to narrow down the search area to an area of a size of about 2 square miles. We then traveled to the site along with the teams of engineers from this wireless carrier, set up Seawave, and after about half an hour of search, located the interferer. The screenshots that I'm showing now show the change in the signal level as Seawave directional log periodic antenna was pointing toward and away from the interferer. So this first screenshot is from the time where we set up Seawave and pointed away from the interferer. The next one is when Seawave was pointing directly toward the interferer. As you can see, there was a rise in the entire noise floor. The interferer was a malfunctioning BDA from a competing carrier that was transmitting signals that leaked into the uplink band used by the tier 1 carrier. The take on all this is that the engineers liked the ergonomic and practicality of Seawave and were impressed as it helped successfully detect and locate interference source that has been disrupting their network quality. In summary, there are 3 points I would like to emphasize on. First, interference does hurt wireless carrier as it is a significant source of customer dissatisfaction of a mobile network. Second, new wireless technologies such as LTE are more negatively affected by external interference at lower signal level than second generation and third generation technology. And finally, interference hunting is an ongoing process, since new and more interferers are continually being created and perturbating networks. On this note, I would like to turn the presentation back to Shenton for the conclusion. Thank you.
Thank you, Mark. So at this time, we will now be taking questions. So if you have questions, we have a few questions already come in, but if you have more questions, please put it in through the questions screen on your webinar. So the first question that we have is, what frequency range can Seawave test? Jim, you want to take this?
Sure. It's really dependent upon the scanner that you have. I mean, we've designed the log periodic antenna to go from 690 to 6 gigahertz. And you can use any Yagi also that you can find off the shelf. So it's dependent upon both the antenna, and then it's also dependent upon what your scanner has in it. So if you have one of the flex scanners from PCTEL, like let's say you have an EX Flex with the super band configuration, you can do 150 megahertz all the way up to 6 gigahertz. If you have an IB Flex, you might have the 570 to 3.8 gigahertz version of it. So, and if you have a fixed band scanner, depending upon what the bands are inside that scanner. So it's dependent upon both the scanner as well as the antennas that you have connected to it.
Another question that we have, and probably I can answer this, is can you test uplink and downlink at the same time for spectrum clearing? Yes, sir. So as I mentioned during my discussion that Seawave can actually do 2 independent scans at the same time. So you can either set it up as uplink and downlink for a particular band, or you can do two different scans on two downlinks or two uplinks at the same time. Excuse me. Another question that we have is, Jim, probably you can take this. How security and infrared cameras interfere?
Yeah, again, it's it's not the actual camera lens that causes any interference. It's the electronics behind it, and you have a lot of different, types of infrared cameras, all the way from very low-cost ones to very high-cost ones, and some of them don't necessarily always. They may be malfunctioning, or they may not be real strict. They had some tested by the FCC, but later ones they changed the manufacturing process. And they can put out signals that are either harmonics or signals that might interfere with a cellular network. But we've actually found security cameras and infrared cameras that have caused interference in networks.
Thank you. Next one that we have is, if I have several Seawaves positioned in different locations, can I combine bearings from them to triangulate where the interferer is? You want to take this, Jim?
Yes, you can. You can post-process the signals later on, and you can actually combine them then to determine where they're at once you get back to the office, and then try to locate where that interferer is.
Mark, probably you can answer this one. Can you record and playback sessions within Seawave?
Yes, this is a good question. You can indeed record and playback session, the entire session with Seawave. You can also export the data. So yes, indeed, you can export and record and replay the data with Seawave.
Next one that we have is, what is the accuracy of the bearing? And can I select which bearings are used for triangulation? Mark, do you want to answer that?
The bearings are, in the automatic mode, the bearings are pretty accurate in the sense that, since you're now in the manual mode, the automatic mode will give you the best level, the best direction for the bearing. So you may take up to more than 3 bearings, 5 or 7, and select the best one and use any 3 bearings to at least do the triangulation. The software can do that automatically for you. You like to add that?
So the last question that I have is, what is the most common type of interferers you have found, or in general that you have been observing?
Usually these days, it's usually 2 types of interferers that you probably find more often. Those would be BDAs or repeaters. And kind of as I mentioned in the webinar, there's a lot of them that have been handed out by the operators, or have been used by people throughout the years, in the 90s and 2000s. And now a lot of the spectrum is being refarmed, and these BDAs and repeaters are not being turned off. So there are a lot of them out there, and they're really causing a lot of interference problems, both in building and outside with macro cells. And the other common source is PIM. The reason why PIM is so common is probably 2 reasons. It's caused, let's say, the rusty bolt effect, dirty connectors, and this type of thing. So a lot of the towers these days, at least the newer ones, are moving more towards fiber optics, but pretty much most of what's been deployed are cables that are actually running up the tower. And these cables have connectors on them, and these connectors are rusting. They're becoming loose because with weather and heat and cold, they start working themselves loose, and they cause PIM. And you're actually finding a lot of PIM also in building, because it depends upon where you place that antenna. Most buildings have a metal infrastructure, and they have ductwork. And if that antenna is not placed properly, you can actually have that antenna radiating the signal into that metal beam or into that piece of ductwork and causing PIM inside the building. So PIM is actually becoming a larger problem in building now, even though it's still a major problem externally also. And hopefully with the use of with more fiber optics in these networks, you'll start to see less and less PIM going forward, but that remains to be seen, I guess, depending upon And I guess maybe that's why you see some of the PIMs starting to move more in building than out building.
Thank you, Jim. So with that, I would like to thank everyone for joining us. As I mentioned earlier, the presentation is recorded and would also be available on YouTube pretty soon for all the attendees. And additionally, PCTEL also has some posters, free LTE posters on physical layer, MIMO, and LTE advanced. If you want any of these posters, just go to our website, which is http://rfsolutions.pctel.com, and you can register, and we'll send you this poster. With that said, thank you, everyone. Good afternoon, good evening, or good night, wherever you are. Thank you.